everyone, welcome to our channel Knowledge Hub. Friends, subscribe to our channel and click the bell icon for the latest update. Today we're going to start with computer graphics, and this is your class 5, as we had done your 4th classes where we had covered up the unit 1 here. And now we had started in the last class, which is your class 4. We had started with unit 2, and now hopefully we will be completing unit 2 in this class. The name of the unit is the unit 2 is your transformation, where we had discussed some of the numerical part as well as some of the theory part in terms of it in the last class. So now we'll go ahead and first of all, it's a huge request from my side to all the viewers. Please go through with the subscribe button and please like, share and subscribe our channel so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. In the same cases, we'll go ahead to start with the question here, that the first question of the session, that what we'll discuss here is that to reflect the polygon whose vertices are -1 0 0 -2 1 0 and 0 2 about the horizontal line, that is y equals to 2, and vertical line x equals to 2, that what we have to solve it out here. So let's go ahead and to solve it out, and the questions I will be writing you here that you can note it down and you can just go through with that as well. So the question is, reflect the polygon whose vertices are -1, 0 0, -2, 1, 0 and 0, 2 about the, first we'll have to find out for the about the horizontal axis or a horizontal line, which is y equals to 2. So here we'll have to find it out for this, and in this criteria, that y equals to 2, on comparing with y equals to 2 with the equation which is your y equals to mx plus c here, and where we'll find it out that m equals to 0 and c equals to 2. So the theta, for that theta we'll be finding out is that theta equals to tan inverse m, and m we had find it out which is 0. So m that is a tan inverse 0, and which is equals to 0 here. So with the reference towards this, that the operation of the reflection through an arbitrary line that is not passing through an origin, that is required to follow the following procedures as well, where in that same cases I'll talk about the formula here, which is t equals to t trans r theta r ref, that is your r theta inverse t trans, that is -1. So here in the same cases we'll talk about the t trans, that is your the translation matrix, r theta, that is your rotation matrix, r reference, that is your reflection matrix, and r theta inverse, which is your that is the inverse rotation matrix, and t trans inverse, which is your inverse translation matrix here. So we'll find it out each and every matrices here, that find it out and to find out the solution as well, and then we'll find it out, and after that we'll put the matrices in this formula, that will find it out the t as well, that we have to find it out in the reflected polygon. So let's go ahead to find it out t trans here, that is we have. So for that t trans matrices we have is your 1 0 0 0 1 0 0 minus c 0, this is which is equals to 1 0 0 0 1 0 and 0 minus 2 0, because c equals to 2 we had find it out here, as you can see. So we had put the value here. So this is your c trans here, But for the r theta, we'll find it out. The r theta here, that is the r theta is your cos theta, and this is your sine minus theta. This is 0 minus sine minus theta, cos minus theta, then we have 0. This is 0 0 1. So the matrix we have 1 0 0 0 1 0 and 0 0 1. So this is the matrix, we find it out. Now for the r reference, we'll find it out here, as that is r reference equals to 1 0 0 0 minus 1 0 and 0 0 1. So this is, we'll find it out. For the another one, that is t trans minus 1, which is equals to 1 0 0 0 1 0 0 3 0. So we'll put the value of c here, that is we had find it out to 1 0 0 0 1 0 and 0 2 0 here. So here this is a matrix here, and then after that we will be having r theta inverse, and that will be finding it out. So we'll go ahead here as well, which is r theta inverse, and for that we have cos theta, sine theta 0 and minus sine minus theta, cos minus theta and 0. This is 0 0 1 here. With this will be equals to, we'll put the value, that is 1 0 0 and 0 1 0 and 0 0 1 here. So in the same reference towards it, we'll go ahead to put the value of t, which we had done as in the form of the formula that we had done here. So let's go ahead to implement that here, which is equals to the matrix we have 1 0 0 0 1 0, क्योंकि अभी हम सारे मैट्रिक्स निकाल चुके हैं. So we'll just simply put the value and then we'll calculate it out. Another matrix is 1 0 0 0 1 0 and 0 0 1. The another one we have 1 0 0 0 minus 1 0 and 0 0 1. Then we have 1 0 0 0 1 0 0 2 0. Then other we have 1 0 0 0 1 0 and 0 0 1 here. When we'll simply solve this, we'll get 1 0 0 0 minus 1 0 and 0 2 and then we have 0, because यहाँ पे सब in between जो है वो 1 है और यहाँ पे minus 1 है. So we'll multiply, we'll get minus 1, and here it is simply minus 2 and this is 2. So minus 2 and that is here 2, that will be multiply and we'll get it as in the form of 2 here. The matrix will be formed like this. Now for the reflected polygon, if I'm talking about that, what we have to talk about it, which is reflected polygon. In a reflected polygon, we have to find out which is minus 1 0 1 0 4 1 1 2 1 and 0 0 1. In this matrix, the other matrix is 1 0 0 0 minus 1 0, which we had to find it out, and that is your 0 2 0, and it will give you minus 1 2 0 0 minus 2 0 1 0 0 and 0 2 0. So it will be find it out here. Now we'll talk about the second one. The second we have here is your, we have to find out for the vertical line where x equals to 2. In a vertical line where x equals to 2 here, for that we'll be finding out, as we know that m is where m equals to infinite and c equals to minus 2. So for the theta that we are finding, theta equals to tan inverse m. So the m we know where is infinity, so the tan infinity is equals to 90 degree. So the 90 degree we place here, and for that we find it out t trans first. the tree trans, we will be finding out the matrix, and that is 1 0 0 0 1 0 and 0 2 0 as well. Now we'll find it out for the another matrix, that is of course for the r theta here, that is r theta equals to cos 9 minus 90 sine minus 90 and 0. This is minus sine minus 90 cos minus 90 0, then 0 0 1, which will be multiplied, and we'll find out the value. Sine minus cos minus 90 is 0, sine minus 90 is minus 1, and that is 0, and sine minus 90 is your minus sine minus 90 is your 1, because that sine minus 90 is minus 1 and minus, and then minus will multiply, so minus minus plus, so it will give you plus value, and then again cos minus 90 is 0 and then 0 here, so that is your 0 0 1 here. So in the same cases, that what we'll find it out, net r refractive, that what we have to find out. So rf is equals to 1 0 0 0 minus 1 0 0 0 1, and for the t trans inverse we'll find it out, that is equals to 1 0 0 0 1 0, and of course 0 minus 2 0 here as well. And for that we'll put the value, before that we'll find out the value, that is of RQ inverse, and that is your RQ inverse, and that we have here the cos here, that is your cos 90 sine 90 0 minus sine minus 90 cos minus 90 and 0. This is 0 0 1. So while putting the value, we will get 0 1 0 1 0 0 and 0 0 1. With the same case, we'll put the value here with the formula, and that is t equals to t trans r theta r theta inverse t trans inverse here as well. Now we'll put the value here, and that is your the t equals to, which is 1 0 0 0 1 0 0 2 0 multiplied by 0 minus 1 0 1 0 0 and 0 0 1. The other matrix we had find it out, 1 0 0 0 minus 1 0, and of course that is your 0 0 1. The other matrix is 1 0 0 0 1 0 0 minus 2 0 here. So then we'll get it the matrix which will be find it out as your 0 1 0 and 1 0 0 0 0 1. The other matrix is your 1 0 0 and 0 1 0 and 0 2 0 here. So the another one for the reflected polygon, will find it out. In reflected polygon, that will find it out here, minus 1 0 1 0 4 is 1 1 2 1, and that is 0 0 1. And for that another matrix that will multiply is your 1 0 0 0 1 0, and that is your 0 2 0, and we'll be getting as minus 1 2 0 0 6 0 1 4 0, and that is your 0 2 0 here. So that will get here as in the form of matrix. Now we'll discuss about the another one, which is to be discussed here. What is shearing transformation, and given an example, so that what we have to discuss here. So in the reference towards this, first we'll discuss about the shearing transformation. In a shearing transformation that distort the shape of an object such that the transformed shape is appear as if the object were composed of internal layers that had been caused to slide over each other is called shear. The first we have is just shear along x-axis. Shear along x-axis. In this, that where x direction shears relative to an x-axis is produced with the transformation matrix, and we will get the matrix along x-axis, the transformation as well. So the matrix will be finding out here is as to be follows. So wasn't that shearing on that, we'll be getting a second one, that is the matrix sh, which is equals to 1 sh x, and that is 0 0 0 0 1 0 and 0 0 1. And for that we will be having the transform coordinates we have for x dash is equals to x plus sh y x, and that is for y dash is equals to y. That will find it out. And any real number that can be assigned to shear the parameter shx, so that will be in the form of, or that the figure would be as in that same cases. This is an x-axis, this is a coordinate 0 0, and this is 0 comma 1, and here it will lie here. This is 0 comma 1, this is 1 comma 0. So in this is an original place when it will be shear, so what it will be gone to ahead, that it will go from here to there. So this is 1 comma 0 as well, and this is your 2 comma 1, and this is 1 comma 1. It will move like this. So that is comes under along the shearing along y-axis here. Now we'll talk about the second one, which we have, that is shearing along y direction. So shearing along y directions here. In this y direction, that shear related to the y-axis is produced with the transformation matrix, and for that we have a shear here that the matrix will be having is in the form of shy is equals to 1 0 0 shy 1 0 and 0 0 1. So in this, that which transform coordinate positions we have x dash equals to x and y dash is equals to x sh dot plus y, and we are sharing with the other line. We'll talk about it here. Another we have sharing with other line. So sharing with other line as well, that what we have to discuss here, and x direction shears relative to a line which is y equals to y ref is generated with the transform matrix, and for that we will be having here is to be as the matrix follows: 1 shx minus shx dot y ref 0 1 0 and 0 0 1 here. So and where the coordinate position for the transformed we have x dash equals to x plus shx y minus y ref and y dash equals to y here. So similarly, a y direction shears are related to a line x equals to x ref that is generated with the transform matrix, and where in the same case the sh ref will be finding out in the form of the matrix is in the form of sh ref, that is equals to 1 0 0 sh y and 1 minus shy x ref and 0 0 1. So this what we'll be finding out, and here with the coordinate for this we'll keep getting is in the form of x dash equals to x and y dash equals to shy, and that is your x minus x ref plus y as well. So that it will be finding out. Now we'll go ahead to discuss about the another question, and that is your proof that the simultaneous shearing in both direction x and y direction as not equals to the composition of pure shear along an x-axis followed by a pure shear along the y-axis. That what we have to see here, and that what we have to even the proof here. So for the question, if I'm talking about, so let's go ahead here as well. So that will be having in the form of prove that simultaneous shearing in both direction, x and y direction, is not equal to the composition of pure shear along the x-axis followed by pure shear along the y-axis. So we know that the simultaneous shearing x and y axis matrix we'll be having here, and that is 1 SHX0, SHY 10 and 001. And for that we will be having the shearing matrix in the x direction. For the x direction we will be getting it in the form of 1 XHX 0, 010 and 001. And for the shearing matrix for the y direction, that will be having 100 SHY 10 and that is 001 here. So shearing with in the x directions and then in the y directions. So what will we get? We'll get the 3 matrix here in the simultaneous way, and that what will go ahead. Which is 1 SHX 0, 010, 001, 100 SHY 10 and 001, which will give you here in the form, that is the matrix I will be writing here. 1 SHX 0, SHY 1 plus SHX SHY 0, 001. Here we'll go ahead with other question, that what we have to solve it out, like show the 3 transformation matrix used to rotate a figure 90 degree anti-clockwise about 3,3, and also generate the transformation matrix, which is of 5 marks. They had asked you about it, so that will be discussed here, and the question I will be writing you for yourself. That is, show the 3 transformation matrices used to rotate a figure 90 degree anti-clockwise about 3,3. Also generate the transformation matrix. And that is of 5 marks that has been asked. So here the rotation about any point that consists of the following step. The first, to translate the point to the origin, then rotate 90-degree origin anticlockwise, and again translate back to the original position here. So for that we will be going ahead to solve it out, and first we will find out the value, and then we'll be going to implement that value in finding out the r 90-degree here, and then we will be go ahead here. So let's going ahead, we'll be finding out again, we'll be finding out the formula first, and that is your r theta p equals to tv r theta and t minus v. So that what we have to find it out. So first we'll find it out for v, that is equals to 3i cap plus 3j cap, that is your the tv will be finding out in the form of tv equals to 103 013 and 001, and for the t minus v, of course, which is equals to 1 0 minus 3 0 1 minus 3 and 001 here. Now for the r 90 we'll be finding out, and r 90 is equals to, which is cos 90 degree minus sine 90 degree and 0, then sine 90 cos 90 and 0 0 0 1. We'll find it out the value here, that will find it out 0 minus 1 0 1 0 0 and 0 0 1. So for that we'll be finding out the value here, which is r 90 here, and that is r 90 will put the value in this particular formula which we had find it out, because tv r theta and t minus v we had find it out the value here. So for that first we'll be writing out this matrix 103 0 1 3 and 0 0 1. The second matrix we'll be writing out as this one 0 minus 1 0 minus 1 0, and then we'll have 1 0 0 and 0 0 1. Then after that 1 0 minus 3, that is your t minus v, 1 0 minus 3 0 1 minus 3 0 0 1 here. So in the same cases we'll go ahead with further one, and that to solve it out. So that will be 1 0 3 0 1 3 and 0 0 1. That will multiply with the matrix, that is 0 minus 1 3 1 0 minus 3 and 0 0 1, and that will find it out. For that is 0 minus 1 6 and 1 0 0 and of course 0 0 1 here. So that what we'll be finding out. Let's go ahead with another one, which is the another question, and that is the also the another important question. Explain transformation between coordinate system and affine transformation. So that we'll discuss here, that the coordinate system and affine transformation that will be discussed here. And first we'll discuss about the coordinate system. In the coordinate system, in a mathematics, the homogeneous coordinate system that allowed to be easily represented by a matrix, and also they make a calculation possible in projective space, just as Cartesian coordinate do in the Euclidean space, and that the homogeneous coordinate of a point of projective space of dimension n, and that are usually written in the form of x, y, z till the colon with w, and a row vector of the length n plus 1, that the other than that we have your 0 colon 0 0 till that, and the two sets of the coordinate that are that is proportional, that denote the same point of the projective space for any non-zero scalar c from the underlying field k, which is cx, cy, cz till cw, that denotes the same point. And therefore this system of coordinate that can be expressed as to be follows: if the projective space is constructed from a vector space v of a dimension n plus 1, that introduces the coordinates in v by choosing a basis and uses this p of v, that the equivalence classes of proportional non-zero vector in v as well. We are taking the example of the projective space of dimensions 3, that there will be homogeneous coordinate, and that the plane at the infinity is usually identified with the set of the points with w equals to 0, and away from this plane we can use as an ordinary Cartesian system, therefore that the affine space complementary to the plane of the infinity, and that is in the terms of it, and in the same cases the infinity is coordinated in a familiar way with a basic corresponding, and that we have in like in the form of we'll be having the coordinates, that is 1 0 0 0 1, and then 0 1 0 1, then we have 0 0 1 1. So here that now we'll talk about the second one, which is your affine transformation. In affine transformation here, that in a computer graphics, that an affine transformation, an affine map from the Latin word affinis, that is connected with between the two vector spaces that consist of the linear transformation followed by a the translation, which tends to be in the form of that is x tends to ax plus b. And in a finite dimensional case, each affine transformation is given by a matrix A and a small a vector b, and of course that which can be written as a matrix A with an extra column b, and an affine transformation that correspond to the multiplication of a matrix and a vector, and composition of a affine transformation that corresponds to the ordinary matrix multiplication. If an extra row is added at the bottom of the matrix that containing only the zeros except at 1 at the right, and that will be having the value is in the form of with the matrix A and B and 0 dot 0, that's from 0 to 0, and that is the here. While an element 1 is added to the bottom of the column vector, which is x and 1, and that is a homogeneous coordinate here as well. In the same reference towards it, an affine transformation is invertible if A is invertible, and that the invertible affine transformation from the affine group, which has a general linear group of the degree n as a subgroup, and is itself a subgroup to a general linear group of the degree n plus 1 here. In the same cases, that the similarity transformation form of the subgroup, that where A is a scalar times an orthogonal matrix, and if the determinants of the A is 1 or minus 1, then the transformation preserves area, and these also form a subgroup that combining both the condition we have the sum tricks, that the subgroup of both where A is a orthogonal matrix, and for each of these groups that have subgroup of transformation which preserve here, that is your orientation, and those where the determinant of A is positive, and in the last case this is your in 3D in the group of the rigid body mentioned, that motion, that the proper rotations and the pure translation as well, where in the same cases we can say that here that A is invertible, A has no eigenvalues of I, and then for all B that the transformation has exactly one fixed point, and there is a B for which the transformation has exactly one fixed point, and a affine transformation with a matrix A that can be written in a linear transformation with some point at an origin. I will discuss some of the things related to the theory here. So now we'll talk about it, as I told you about it, windowing, and that we'll discuss in a detail. And in the windowing, that the window is a rectangular separation of the viewing scene, which define that the top, bottom, and a side, or a left side, or a right side, that clipping planes that relative to the observer camera positions as well. And in the same cases, a window, then it will be mapped, and then after that the viewport will be seen here. So that the start with the 3D scene, then when it's projected to a 2D scene, and 2D scene is infinite plane window, which is the device has a finite visible rectangle. So there is a need to map the rectangular region window of the 2D scene to device viewport as well. In the same cases, we'll discuss about the window, which is a rectangular region of the interest in scene, and the viewport, a rectangular region on the devices, as well as viewing pipeline. We'll see where MC, then WC, VC, and VC and DC. There is MC stands for the modeling coordinate, WC stands for world coordinate, and VC stands for viewing coordinate, and VC is your normalized viewing coordinate, and DC is your device coordinate here. In the viewing transformation, that the process of mapping a part of WC scene that to the DC is called a viewing transformation. It includes the following step, like first we have to translate the window to the origin, then we have to scale the parameters SX to SY, and then translate to a viewport as well. In a 2D clipping algorithm, where the clipping removes the point outside a region of interest, and that is discard, that is a part of primitive and outside on window, and point clipping as well, that remove the point outside the window, and edge joints is either entirely inside the region or not, and line clipping, which removes the portions of the line segment outside the window as well. Where a line clipping is completely visible if both of its end points are in the window. And line clipping algorithm, that the types are, that is the Cohen-Sutherland line clipping algorithm, Liang-Barsky algorithm, and line clipping against the non-rectangular clip window as well. In the same cases, here we'll talk about it with the detailed here, and that is in the terms of it. So we will discuss about the line clipping against the non-rectangular clip window, and the Polygon clipping algorithm we'll discuss, which is the Sutherland, Hodgman, Polygon clipping, and the Wemos and the Atherton Polygon clipping, and of course the curve clipping as well. In the term of the text clipping, we'll discuss the user's following steps, which is all or none string clipping, all or none character clipping, and clip the components of the individual character. That what we'll discuss here. First of all, we go ahead with the discussion about it, which is the what do you understand by the term clipping and windowing. So first we'll discuss about clipping and windowing in a detail. So here in the clipping and windowing here, in the terms of it, if I'm talking about, so first we'll discuss about clipping, then we'll discuss about windowing. In clipping, that the clipping is the method to cut on a specific object, and the object may be point, line, area, or a text. In other words, we can say that any procedure that identifies those portions of a picture that are either inside or outside of a specific region of space is referred to as clipping here. But windowing, if I'm talking about, the any convenient Cartesian coordinate system is known as a world coordinate system, and when we select any specific area from the world coordinate system, it is known as windowing. And an area on a display device to which a window is mapped is called, that is your window point here, that is a viewport. And a window and a viewport that are rectangular in standard position and with the rectangular edges that parallel to the coordinate axis. In the computer graphics, windowing is referred to as a selected area of the picture for viewing here as well. Now we'll discuss about more in detail, which is what do you understand by the term concatenations of transformation here. So in concatenation of transformation, that what we'll discuss here. Concatenation of transformation. In concatenation of a transformation here, where concatenating transformation, where the single transformation that can be combined as a sequence that is your the sequence of transformation, and this is called concatenation, and that the combined transformation that are called concatenated transformation. And during the editing process, when a graphic model is being developed, the use of the concatenated transformation is quite common, and it would be unusual that only a single transformation that would be needed to accomplish a desired single transformation that would need to accomplish a desired manipulations of the image. Where the two examples of your combinations manipulation of the image, we have that the two examples were the combination of transformation that would be required would be, and that is the rotations of the element of and about an arbitrary point in an element, that magnifying the element but manipulating the location of one of its points in the same location. And in the same case, in the first case, if I'm talking about that the sequence of the transformation, that would be translation to the origin, and then the rotations about the origin, and then the translation back to the origin location as well. In a second case, that the element would be scaled or magnified, followed by a translation to locate the desired point as needed. The objective of concatenation is to accomplish a series of image manipulations as a single transformation, and this allows the concatenated transformation that to be defined more concisely, and the computation that can be generally accomplished more efficiently as well. To determining the concatenation of a sequence of single transformation, that can be fairly straightforward if the transformation are expressed in matrix from as we have done. For example, if we want to scale a point by a factor of 2 and is a two-dimensional system, and then rotate it about the origin of by 45 degrees, the concatenation would simply to be a product of the two transformation matrix, and it is important that the order of the matrix multiplication be the same as the order in which the transformations are to be carried out, and the concatenations of the series of a transformation that becomes more complicated when a translation is involved as well. Now we'll discuss more about in the detail, which is what do you understand by the world coordinate system. In the world coordinate system here, that the objects are placed into the scene by a modeling transformation to a master coordinate system that is referred to as a world coordinate system, which is WCS. And the world coordinate system is a space in which the picture is defined, and a rectangular window with its edge parallel to the axis of the world coordinate system is used to select a portion of the scene for which an image is to be generated as well. In the same cases, where the sometime an additional coordinate system called the viewing coordinate system is introduced to stimulate the effect of moving and or tilting the cameras as well. Now we'll discuss about another question which has been asked of 10 marks here in AQ2 and as well as your examination paper as well. That is, what do you understand by a normalized device coordinate system, or that has been asking them or a few point, like that is what is window to viewpoint coordinate transformation, and what are the issues related to the multiple windowing. So that what they had asked you about it here. So first of all, we'll discuss about the normalized device coordinate system, that is your NDCS, and then we'll discuss about the viewing transformation, then workstation transformation, then window to viewpoint mapping. That we'll discuss about it here. So let's going ahead to discuss about normalized device coordinate system. In in a normalized device coordinate system here, that is an image representing a viewpoint. A view often become a part of a larger image, like a photo on an album page, and which models the computers that monitor display area. And since the album pages vary and monitor sizes differs from one area, and since album pages vary and monitor size differ from one system to another, so we want to introduce a new independent tool to describe the display area as well. And the tool is called the Normalized Device Coordinate System, which is your NDSCS, that is Normalized Device Coordinate System here, in which the unit 1 cross 1 square whose lower left corner is at the origin of the coordinate system that defines the display area of the virtual display devices, where a rectangular viewport with that axis parallel to the axis of the NDCS is used to specify a separation of the display area that embodies the images as well. Now with the same we'll talk about for the viewing transformation here. In viewing transformation here, that the process that converts the object coordinate in WCS to normalized device coordinate is called window to viewport, so that is mapping here. Now I'll talk about the workstation transformation. In workstation transportation here, that the process that maps normalized device coordinate to discrete device or image coordinate, that is called a workstation transformation, which is a second window to viewport mapping with the workstation window in a normalized device coordinate system and the workstation viewport in the device coordinate system. Collectively, these two coordinates mapping operations are referred to as a viewing transportation. Workstation transformation is dependent on the resolutions of the display device frame buffer as well. We'll talk about another one, which is window to viewport mapping. Window to discussed about it, which is your window to viewport mapping. So in this we'll talk about it, which is a window is specified by a 4-word coordinate, that is Wx here, that is for the min and the max as well, and similarly a viewport that is spec for the 4 normalized device coordinate, and that the object of the window that is a window to viewport mapping is to convert the world coordinate of an arbitrary point to its corresponding normalized device's coordinate, and that in order to maintain the same relative placement of the point in a viewport as that window that we required of. And in the same cases we'll go ahead to solve it out as well to find out the representation of n as well. So where in the same cases you have to go through with that and you have to understand what it follows. So we have Wx minus Wx min upon Wx max minus Wx min, which is equals to Vx minus Vx min upon Vx min, and that is your Vx max minus Vx min, and we can say that Wy minus Wy min upon Wy max minus Wx min, and that is your in the same cases, and that here with y, so it is Wy min, and that is your, of course, that it's Wy max as well, and that is equals to Vy minus Vy min upon Vy max minus Vy min here. Thus we can say that here the Vx equals to Vx max minus Vx min upon Wx max minus Wx min, where Wx minus Wx min, and that is plus Vx min. And for the Vy, talking about Vy, that is Vy equals to Vy max minus Vy min upon, that is your we have Wy max minus Wy min, which is your Wy minus Wy min Vy min as well. So it can be represented in the form of, that is Vx Vy1 equals to n dot Wx Wy1, and for that we'll find it out for the n here, and that is n equals to 10 Vx min and 01 Vy min and 001 here. For that we'll be having here, that is your Vx max minus Vx min upon Wx max minus Wx min, 0 and then 0. So here this is 0. Second coordinate is Vy max minus Vy min upon Wy max minus Wy min, that is 0. Then this is 0, 0 and 1. For after this we'll be calculating the other matrix as well. We'll get it 1 0, that is minus Wx min 0 1 minus Wy min and then 0 0 1 here. So this is what we'll find it out, and after that we'll find out for Sx, Sy and then n. We'll find out the coordinate of n as well. So here let's go ahead here. So here we'll have Sx Vx max minus Vx min upon Wx max minus Wx min. We're talking about Sy, so that is the Sy is equals to Vy max minus Vy min upon Wy max minus Wy min, and now finding out for the value n, which is equals to 1 0 Vx min 0 1 Vy min and 0 0 1. With the same case we'll have another matrix as well, which is your Sx 0 0 0 Sy 0 0 0 1, and that is the another matrix we have here. It's 1 0 minus Wx, then 0 1 minus Wy x, and of course the another one is your 0 0 1. So this is the matrix what we will find it out. So here we'll go ahead with other question, and that what we have to solve it out, and even though that has been asked in their examination paper as well. So the question is, find the complete or viewing transformation that maps a window in a world coordinate with x extent 1 to 10 and y extent 1 to 10 on a viewport, with the x extent 1 by 4 to 3 by 4 and y extent 0 to 1 by 2 in a normalized device space, and then maps to the workstation window with an x extent 1 by 4 to 1 by 2 and y extent that 1 by 4 to 1 by 2 in the normalized device space into the workstation viewport, with x extent to 1 to 10 and y extent 1 to 10 on the physical display devices. So that you have to solve it out, the parameters for the normalized transformations that we have to solve it out here. So for that, first of all I'll repeat the question because it's too long. so you can get to know about it. That is to find the complete viewing transformation that maps a window in a world coordinate with x extent 1 to 10 and y extent to 1 to 10 on a viewport with x extent 1 by 4 and 3 by 4 and y extent 0 to 1 by 2 in normalized device space, and then maps a workstation window with an extent of 1 by 4 to 1 by 2 and y extent from 1 by 4 to 1 by 2 in a normalized device space into a workstation viewport with x extent 1 to 10 and y extent 1 to 10 on the physical display devices. For that, we'll have to solve it out. Let's go have a solution here. So solution for this, for the parameters of the that is the normalized transformation we have as they had given you. So for wx min we have 1 equals to 1, and that is wx max will be your 10 from 1 to 10 they had given you, so the 10 max is 10. Wy min is your of course 1 and wy max is your 10 here, and in the same case vx min we have 1 by 4 and vx max is your that is of 3 by 4. Vy min is your 0 and Vy max is your 1 by 2, and where Sx if I'm talking about, so that is 1 by 2 upon 9 and that is equals to 1 upon 18. It will नीचे चला जाएगा, 9 2 is 18, so 1 upon 18 here. For that we'll finding out the another one which is your Sy here. So in the case of the Sy we'll talk about and we'll find it out as well. So the Sy equals to 1 by 2 upon 9 and that is will multiply, that is you will get your 1 by 18 only, and then now we'll find it out for the n here, that is n equals to 1 upon 18, 0, 7 upon 35, sorry 7 upon 36, then this is your 0, 1 by 18, minus 1 by 18, 0, 0 and 1. For the parameters for the workstation transformation as will represent it here, so for that we have wx min will be equals to 1 by 4, wx max is equals to 1 by 2, and your that is wy min is equals to 1 by 4, wy max equals to 1 by 2, then vx min equals to 1 and vx max equals to 1 by 10, and vy min equals to 1 and vy max equals to 10 here. So for that Sx here, that is Sx is equals to 9 upon 1 by 4 and that is equals to 36, and Sy is equals to 9 upon 1 by 4, so that will be equals to 36. 9 is 4 is going to go up and multiply, and so 9 4s are 36, so that will find it out here. For that w equals to we have 36, 0 minus 8, the other coordinates is 36 minus 8 and 0 0 1. The complete viewing transformation for the v we will be going ahead, and that is the formula for v is your w dot n. So w we had find it out and n even though we had find it out, so for that we have 36, 0 minus 8, 0 36 minus 8 and 0 0 1, and the other matrix is 1 by 8, 1 by 18, 0, 7 by 36, the other is your 0, 1 by 18 and that is 1 by 18 minus 1 by 18 and that is 0 0 1. When we'll solve it out, we'll get a matrix that is your 2 0 minus 1, 0 2 minus 10 and 0 0 1 here. So this will be finding out here. Now other than that, we will go ahead with the further one, and that what we'll discuss is, and in the same cases, that is to write any one line clipping algorithm, we have to write one line clipping algorithm, and that has been asked in many times in the examination paper of 6 marks and 10 marks as well. So in the same cases, the question has been write any one line clipping algorithm, that has been asked of 6 marks, write Cohen and Sutherland line clipping algorithm. तो अभी इससे पहले बोला था कोई भी क्लिपिंग एल्गोरिथम बता दो, अभी पूछा गया है कि आपको कोहेन एंड सदरलैंड लाइन क्लिपिंग एल्गोरिथम बताना, जो कि आपका 5 मार्क्स में पूछा गया है. द अदर क्वेश्चन इज दैट टू डिस्क्राइब द कोहेन सदरलैंड लाइन क्लिपिंग एल्गोरिथम विद सुटेबल एग्जांपल. सो यहाँ पे कोहेन सदरलैंड लाइन क्लिपिंग एल्गोरिथम पूछा गया है, जो कि 6 मार्क्स का पूछा गया है. So this is another way. So we'll be going to discuss about the Cohen-Sutherland line clipping algorithm, जिसमें ये आपके तीनों क्वेश्चन को इंक्लूड कर देगा. For that Cohen-Sutherland line clipping algorithm here, in this algorithm a rectangular window is to be considered whose coordinates are like x w min and y w min and x w max and y w max to be shown, and that what will go ahead here to the descriptions here. So the question we have, that is to be Cohen Sutherland line clipping algorithm. So in this what we have to go through with that, and the we had mentioned about the min and max as well. So in that, every line and point is to be assigned a 4-digit binary code, that region code, and that identifiers the location for the point corresponding to the boundaries of the clipping window, and the procedure for the calculating the endpoint, which is of px comma y, and that code is to be followed. So for first bit, for the bit 2, for the bit 3, and for the bit 4, that has been pointed out, and we'll go ahead with each and every bit here. So we'll with that same cases, we'll go ahead here, and in the here, that is for bit 1, for bit 2, for bit 3, and for bit 4. So here with this same reference towards it, and that is to discuss here, and that is if y minus y w max is less than 0, then code equals to 0, else code equals to 1. For the bit 2 here, that if y min minus less than 0, then code equals to 0, else code equals to 1. Here for this, if x minus x w max less 0, then code equals to 0, else code equals to 1. For bit 4 here, that if x w min minus x less than 0, then code equals to 0, else code equals to 1. If the region code of both the endpoints of a line segment is 0, 0, 0, 0, then the line is completely visible as it's completely aligned within the window. And if the region code of both the endpoints of the line segment AB is that not 0, 0, 0, 0, we find an AND of both the points A and B. If the results of the AND operation is 0, 0, 0, 0, that the line is partially visible, and we need to find the point of intersection, and the intersection point with the clipping boundary that can be calculated to be as follows. If x1 and y1 and x2 and y2 that are the endpoints of a line segment, then that of the y coordinate that intersect the point with a vertical boundary that can be obtained here. And for that, if x1 and y1 and x2 and y2 that are the endpoints of the line segment, then the y coordinate of the intersection point with a vertical boundary that can be obtained here. So that will be find it out in the form of the equation, which will be getting is your y equals to y1 plus m x minus x1, where the values of x is a set of either x equals to x w min or x equals to x w max here. And similarly, we find the intersection point with the horizontal boundary if after an operation that the results not 0 0 0 0, then the line completely lies outside the clipping window here, so that it follows here. So first of all, when you are going to consider about these type of a question, you have to be very clear about it, and you have to very understood about it what you are doing, because this is sort of a typical subject, and that is some of the students, even though not getting very clearly, that's the reason I will provide you this particular subject, which is your computer graphics here. Let's go ahead with another topic here. That is another question. So here we'll end up with this class, and that is in the next coming class we'll end up with this unit as well. So here we'll end up with this unit, and now we're going to start in the next coming class. We'll end up with this unit as well, the unit 2 of the computer graphics, and then we'll continue with the next unit as well, that is your the 3-dimensional here. In this subject we have only 4 units, and we'll discuss the short answers question as well. So in the first unit we had completed the graphics devices, which is to introduction, the line generation, types of the computer graphics, graphic displays, random scan displays, raster scan display, frame buffer in a video controller, points and lines, line drawing algorithm, circle generating algorithm, midpoint circle generating algorithm, and a parallel versions of these algorithm as well. The second unit we had completed, which is just transformation, with the transformation, basic transformation, matrix transformation, and homogeneous coordinates, composite transformation, and even the reflections and shearing, windowing and clipping, viewing pipeline, viewing in transformation, 2D clipping algorithm, that is a line clipping algorithm such as Cohen-Sutherland line clipping algorithm, Lian-Baski algorithm, line clipping against non-rectangular clip window, Polygon clipping, Sutherland, Hodgman, that is Polygon clipping. And then of course we had discussed about the Weller and Atherson, that is a Polygon clipping, and curve clipping and a text clipping as well we had done, we will have to done here. And that is your unit 3rd. We had to start with the 3-dimensional, which is a 3-dimensional 3D geometric primitives, 3D object representative, 3D transformation, 3D viewing, projections, 3D clipping as well. Then after that we'll start with the unit 4, which we have to cover up the curves and the surfaces. And the curves and the surfaces, the quadratic surfaces, the spheres, ellipsoid, blobby objects, introductory concept of spline, B-spline, Beziers, curves and surfaces, hidden line and surfaces, backface detection algorithm, depth buffer method, a buffer method, and that is the scanline method, the basic illumination models, ambient light, diffuse reflection, spectacular reflection, and a Phong model, combined approach, Warn model, intensity attenuation, color consideration, transparency, and shadows as well. And we'll have to discuss about the very short answer type question as well. So here we have a request, please go through with the subscribe button, and please like, share, and subscribe our channel, so that many and maximum people can get the information at once. And even though you can also enjoy the video as well, you will be provided each and every subject which we are doing, that is your computer graphics. We are doing quantitative aptitude and database management, as well as data warehouse and data mining. PPL we had completed, that is your principle of programming languages, and that will start with the managerial economics as well. And we are doing simultaneously the reasoning classes as well. So please go through with us and stay tuned with us. Thank you. Hope you enjoy this video. If you like this video, please give a thumbs up and give a suggestion and a comment box. Thank you.